Great. So welcome to Air Quality Sensor Bootcamp. This is our first time running a bootcamp here at Clarity. We've done a lot of educational webinars and workshops in the past, but it's our first time doing this comprehensive bootcamp, which is intended to give you all the knowledge you need to start working with air quality sensors. And just a brief introduction to Clarity for those of you who aren't familiar with us. If we could go to the next slide, Jack. So you'll learn a lot more about us and the work we do throughout this boot camp. But just as a brief introduction, we have a comprehensive air quality sensing solution. We provide our sensors as a service, which is a little bit different from a lot of the folks who operate in the industry, and we'll get into why we take that approach throughout the sessions. But briefly, we're working in more than 70 countries around the world with government agencies, communities, businesses, all types of people who are looking to collect air quality data at scale. And we're hoping to share some of the knowledge we've learned through that work with all of you through these sessions. We go to the next slide, please, Jack. So just a reminder, this is the first of 3 sessions that we'll be holding throughout June, and we've structured these in a way that we think, will help bring you from, the fundamentals of air sensors, what is the technology, how to use it, to what are some of the use cases that we've seen people using sensors for around the world, and then finally network design, so the actual implementation of air quality sensors and what we see sensors being used effectively for is not just for 1 or 2 measurement points, but really collecting air quality data at scale is where air sensors really shine. So we're going to really focus on how to design a network of sensors in that 3rd session. And just a couple of housekeeping items before we dive into the content with Jack here. If we can go to the next slide, please, Jack. So if you haven't already, make sure you're registered for all 3 sessions. I think each of the sessions will be valuable on their own, but if you complete all 3, it's really going to give you the comprehensive knowledge you need to get started with air quality sensors. So we would recommend registering for all 3 if you haven't already. Secondly, would encourage everyone to join the Slack channel we created for the bootcamp. So during the live sessions, we'll be communicating through the chat and through the Q&A on Zoom. But in between sessions, we wanted to create a space for all of you to continue to engage with instructors, with each other. We think that the more collaboration that happens throughout this program, the more effective it will be for all of you and the deeper the learning will be. So please do join the Slack channel. And I think Clance just shared a link in the chat. Thanks, Clance. And lastly, so, we do have the live sessions, but we want to provide additional learning, materials throughout the program in between the live sessions. So we've actually put together some homework assignments. They're really brief, just 15-20 minutes is all it should take, but really encourage you to complete the homework assignments. These will be shared the day after the live session, both through email and through the Slack channel. And if you submit all 3 homework assignments to Clarity, we will be able to provide a certificate of completion of this bootcamp. So just would encourage everyone to complete the homework if your schedule allows. I think it'll really help deepen the learning from these live sessions. And that's it from me. We'll get into the exciting stuff now with Jack and hand it over to you, Jack.
Cool. Thanks for the introduction, Ryan. Hello, everyone. I'm really excited to speak with you today. As Ryan mentioned, my name is Jack Kodros. I'm an air quality data scientist here at Clarity. My science background is in atmospheric chemistry and physics. And at Clarity, I work on researching the science of air pollution, the science of low-cost air quality sensor calibration and performance, and the science of air quality monitoring in general. Today, really excited to talk about a brief overview of air pollution, and more importantly, how we think about air pollution and how we categorize it. Next, we'll do a brief overview of low-cost sensor technology, and importantly, how it differs from regulatory instruments and when and where we might want to use low-cost sensors to maximize the benefit of them. Finally, we'll talk a little bit about data quality and calibration. And at the end, we'll have plenty of time for Q&A. There is a chat. Feel free to drop your questions in the question panel. Ryan will be monitoring them, and we can go over them at the end. So I just wanted to mention here at Clarity, we recently formed what we call the Clarity Lab. And we think of this as a science and research group we have within Clarity, where we can take a scientific approach to enhancing sensor performance. Our goals are to explore long-term scientific questions regarding air quality sensing. And really importantly, we want to understand how and where sensors perform in different environments, what climates they perform well in, what climates they don't perform well in, what seasons, what time of day. This allows us to communicate with our customers and our partners in their air quality monitoring projects, accurate information and insights on when and where sensors will perform the best and how they can leverage that data to get actionable insights in their community. Finally, of course, we'll discuss a lot of low-cost air quality sensor limitations, but given that there are limitations, we of course want to improve them. So we work a lot in improving sensor performance through different calibration methods by looking into hardware and software innovations. So with that, let's go ahead and get started. I wanted to start by thinking about why we care about air pollution. And for one of the biggest reasons we care about air pollution is from a health standpoint. A number of studies has shown that increased exposure, and especially long-term exposure to air pollution, can increase the risk of premature mortality. The Global Burden of Disease study estimates that approximately 7 million premature deaths each year are due to the effects of air pollution, and this is globally. About half of those are from outside air pollution or ambient air pollution, and the other half is indoor or household air pollution. We'll go a bit more into ambient and household terms a little bit later. In addition to increased risk of mortality, there are a number of other adverse health outcomes that affect our day-to-day lives. These sometimes get a little less attention in newspapers, but they're still important in deteriorating quality of life and impacts to the economy. These can be things like asthma attacks, respiratory illnesses, itchy eyes, itchy noses, things that lead to days of missed work and school. In addition, there are important questions about equality, environmental justice, and environmental racism as it relates to air pollution, both in the United States and globally. The risks of exposure and harm are not equally distributed. Disadvantaged communities and communities of color in the United States have been shown to be exposed to higher levels of air pollution. In addition, people of different age groups, like the children and elderly, are often more susceptible to the health outcomes of air pollution. In addition, people with pre-existing conditions, especially respiratory conditions, are also more susceptible to health outcomes of air pollution. Finally, climate change is an ever-present issue. We hear a lot about carbon dioxide and methane, which are, of course, air pollutants themselves, and they have the largest climate impacts. But a number of the other urban air pollutants also have climate impacts, such as NO2, ozone, and PM2.5. And actually, PM2.5 is the largest uncertainty we have about climate forcing. So while CO2 and methane have the largest climate forcing, PM2.5 actually has the biggest question mark next to it. So let's take a step back and just look at what is air pollution. A broad definition is air pollution is a mixture of natural, man-made, and man-made by anthropogenic substances in the air that can cause harm. That's a really broad definition. I understand that. So it's helpful to think about air pollution and break it down into different categories. So one category that's often discussed for air pollution is by source, and this can be natural or anthropogenic. So by natural, I mean things like volcanic emissions, pollen that causes allergies, or a dust storm. Anthropogenic, I mean human activities, and these can be anything ranging from cars, trucks, power plants. We can even subdivide human activities into a new category, mobile sources. So let's say cars, tractors, anything moving, or stationary sources as it's described, anything staying still, like a power plant, metal factory, anything of that nature. Another common category is where exposure occurs, and I mentioned this a little bit already. You could be exposed to air pollution outside, and so this can be any urban background emissions, traffic emissions, things you get at the roadside, anything when you leave your house. Or there can be emissions that you're exposed to indoors, and this can be heaters, gas stoves, cooking emissions. When you vacuum your rug, you often emit dust particles. Of course, ambient and outdoor are somewhat related. If you open your window during a wildfire smoke episode, you have outdoor emissions that are coming indoors. Finally, there's another category, origin. This is a bit more chemically complicated, but I think it's important just to mention. Some pollutants are considered primary pollutants, and what that means is they're emitted directly in the chemical composition that they exist in the atmosphere and as we measure. So for instance, we emit carbon monoxide, it stays in the atmosphere as carbon monoxide, and we measure it as carbon monoxide. Secondary pollutants are pollutants that are formed in the atmosphere from other chemical components. Ozone is a great example of this. Ozone is not emitted directly from cars. It is formed in the atmosphere from emissions from different chemicals that are emitted from cars. This is really important when we think about air quality monitoring. Ozone may not be highest next to emission source. It might be highest downwind after it is formed. Finally, we really need to think about the state of matter, and I'm going to discuss this more detail in the next slide. But in terms of regulatory applications, health applications, and important measurement technology will be different if the air polluted is a particle or a gas. So let's think about that in a little more detail. So air pollution is commonly subdivided into particles and gases. And again, this is important because it changes how we regulate the pollutants and it changes the technology we use to measure them. So air pollution that is in the form of particles is commonly called particulate matter. Sometimes you'll see aerosols. That's become more of a technical scientific definition in the climate science field. In air pollution and health, we typically say particulate matter. This definition is any solid or liquid particles that are suspended in air. It's important to remember it can be any chemical composition. So it includes dust, pollen, black carbon, the black and organic carbon that make up soot, sea salt, and often some liquid water is mixed in as well. Particulate matter can vary in size, composition, and emission source. In terms of regulation, particulate matter is regulated by size, not by composition, by size. So there are two broad size cutoffs, PM10, which is the relatively larger size. We call these coarse particles. And the definition are particles with a diameter that's smaller than 10 microns. Most of these emissions, not all, but commonly most, come from mechanical processes like road wear, construction, dust storms. If you brake suddenly on the highway, little bits of your tire will be emitted as PM10. The smaller size cutoff, or the relatively smaller size cutoff, is PM2.5, or fine particles. These are particles with a diameter less than 2.5 microns. And these typically, not all, but typically come from combustion sources like cars, cooking, power plants. I've been trying to emphasize relatively larger and relatively smaller because, of course, all of these particles are absolutely tiny. The diagram on the left is trying to show this. PM10, PM2.5 are both so small that they are a small fraction of the width of a human hair or the width of a grain of sand on the beach. So the other category are gases. And now gases are regulated by chemical composition. So gas chemical compositions could be nitrogen dioxide, which usually comes from combustion. A lot of it's from cars in urban environments. ground level ozone, which forms from other pollutants. It's a secondary pollutant. Just to keep in mind, ozone at the surface is toxic for us to breathe in. Ozone very high in the atmosphere above where planes fly protects us from ultraviolet radiation. So ozone at the ground, air pollutant, it is bad. Carbon monoxide is another pollutant, and SO2 as well, sulfur dioxide. Together, these are the criteria air pollutants, in addition with lead, with which we're not showing. The criteria air pollutants are what the US EPA regulates from a health standpoint. So before we dive into more details about air pollutants and air quality sensor technology, I wanted to mention a number of questions we usually think about when starting to design an air quality monitoring project. I'm going to go into detail on 1 and 2 of these, and I think the other panelists will go into detail on the rest of them as well. So number 1 is what I'm going to talk the most about. How much air pollution is in the air? We simply want to understand the amount of air pollution and quantify it. Second, where is it going? Is it going to be transported by wind? Is it going to undergo chemical reactions and change? That's another thing we need to understand. Third, what's the air pollution composition? What are the chemical components? What are the states of matter? 4, what are the air pollution sources? Are they indoor? Are they outdoor? Are we expecting them to be similar to wildfires or power plants? Are they stationary or mobile? 5, who wants the air quality data and why? This is really important in terms of communication and outreach and how we understand the data and what data we might want to provide. 6, who will be breathing it in? Is it people we expect to be more susceptible to the health outcomes of air pollution? Is it people in disadvantaged communities? Are there questions of environmental justice we need to consider? 7, when does exposure occur and for how long? We commonly think that health impacts are often related to the length and type of exposure. And finally, what kind of data and what action is needed to improve the situation? When we do an air quality monitoring project, we often want to end with actionable insights. So let's go back. Excuse me. I mentioned that one of the big questions I want to look at today is how much air pollution is in the air. At the base, this is the most central question when monitoring air pollution. So how do we quantify air pollution? We can quantify it in 2 and likely more similar ways. One is concentration, and concentration, of course, is the physical amount in the air. It is literally the pollution reported as a unit volume of air. And by unit volume of air, I mean if you could imagine a box of air, and then you were going to consider all the pollution in your box, that would be the concentration. The units by convention can be different for different pollutants. But it's important to remember they're all physical and we can convert between them. So for instance, one common unit for particulate matter is mass concentration. This is micrograms per cubic meter. The micrograms is describing the mass of the particles. And micrograms, remember, humans, we often weigh ourselves in kilograms. If we were in Europe, of course, in the United States, we do pounds, but kilograms would be a unit of measure for humans. For particulate matter, it's all the way down at micrograms. And the per cubic meter is referring to that imaginary 1 cubic meter box of air. So that's common for PM 2.5, and you'll see that in regulatory documents. Instead of considering the mass, you can certainly consider the number per cubic meter. That's just the number of particles in your box. We put mass and number, that's the most common for regulation, but scientific research certainly considers surface area, concentration, volume concentration, whatever helps you understand your air quality problems. For gases in the US, we typically, by convention, report them in mixing ratios. And a mixing ratio is simply the volume of the pollutant per volume of air. Now, fortunately, air pollutants take up a tiny fraction of our air. So we then scale them by the billion or by the million. So parts per billion is describing the volume of a pollutant per volume of air scaled to the billion. We can also scale to the million, and you see less often, but you can also have PPT, parts per trillion, whatever scaling gives you the most easy to understand number. That's all we're doing. In Europe, gases are reported in the same way as PM 2.5 commonly, micrograms per cubic meter. Again, the specific units are often done by convention for convenience. We can convert between them. They're all physical quantities. Now, on the right-hand side is an air quality index. This is taking the physical concentration and translating it into health outcomes. So for instance, an air quality index of 0 to 50 is the concentration where the air quality is considered good enough to breathe, healthy, will not provide any adverse health outcomes. Once you start getting above 100, that is the concentration in which breathing it in is unhealthy. Again, we can go back and forth between concentration and air quality. Here at Clarity, we often provide and discuss both of these metrics. So now we've talked about the units, let's start to jump in about measurements themselves. And here I want to compare and contrast reference instruments and low-cost sensors. So reference instruments, you'll sometimes see terms like federal reference method or federal equivalent method. The federal reference method is the actual instrument that's used for regulatory purposes. These instruments are more expensive. These are tens of thousands of dollars instruments in US dollars. For that price point, they better be and are often highly accurate and highly reliable. They're used in regulatory monitoring. Now, that said, they're highly sensitive and complex scientific instruments. They require trained professionals to operate, and they require regular maintenance. And this can be calibration, cleaning, replacement of parts. So reference instruments are highly accurate and reliable so long as they're being operated and maintained correctly. Now let's go over to low-cost sensors. These are becoming more and more commercially available. They're less expensive, hundreds to thousands of US dollars. Now at that price point, they also are limited. They're less accurate and less reliable. But some of the benefits of them is that they're often used in citizen science projects. You don't need to be a trained technician to operate them. They're easier to use and maintain. They're smaller, portable. Our Clarity nodes come with a solar panel, so they don't need to be plugged into a power source. They may not require as much maintenance, but they do require specific calibration checks to ensure accuracy. So one of the key things I want everyone to take away from this talk is that there is no free lunch. You can't have a very low, inexpensive instrument and have the same accuracy and reliable as an instrument that costs tens of thousands of dollars. But there are benefits. It is often beneficial to have something that's easier to use and maintain, that's easier to deploy. And it's that cost-benefit trade-off that we'll discuss for the next few slides. So first, I kind of want to go into where and when we can use and make the most benefit of low-cost air quality sensors. So here I'm showing a map from the EPA showing PM 2.5 monitors in the United States. Now, the EPA has done a fantastic job increasing the network of regulatory and reference instruments. Compared to most other countries, this is a fantastic network and it's a great data source. However, we can already see that there are gaps in our measurement system, our measurement network. For one, rural areas, many of them have no measurement reference instrument. Almost 2/3 of counties in the United States have no air quality measurement infrastructure whatsoever. Now, all that said, we can see many of the populated areas do have a reference instrument. And at first glance, this seems highly encouraging, and it is. This is a great network. But if we zoom in, we can start to see some gaps in this network. Here's an example from San Francisco. So the entire city of San Francisco has one regulatory instrument located in downtown San Francisco. And if you take a look at the geography of San Francisco, we have Golden Gate Park, we have the Pacific Ocean, Golden Gate Bridge, highways, the Bay Bridge, downtown Chinatown. It's highly unlikely that one monitor located in one location is able to capture the spatial variability of air pollution in San Francisco. This is kind of a personal map for me because my parents live out in the northwest corner of San Francisco. If I want to see what air pollution they're being exposed to, the monitor that's located all the way on the other side of the city is likely not representative of what they're experiencing over out in the northwest corner. So the issue with sparse monitoring networks is that they can miss localized air pollution events and conditions that may be affecting neighborhoods that don't have a regulatory instrument. So for instance, and this is just a hypothetical map, if you had a regulatory instrument located in one neighborhood, but let's say a localized emission source like a power plant or even a wildfire plume passing over a neighborhood, this instrument may completely miss this air quality event. It may report that air quality is fine, yet some people in these communities are going to be exposed to much higher concentrations. However, if we supplement the regulatory instrument with additional monitors, we can then start to see a gradient throughout the city, and we can understand the air pollution in different areas. So this is really where we see the most benefit of low-cost sensors, not in replacing regulatory instruments, but supplementing them to improve the spatial distribution of our understanding of pollutants. So while traditional monitoring can only have a few sites and give you broad swaths of air pollution spatial distribution, a dense network can offer more fine scale and better understanding of the air pollution in local communities and neighborhoods. Again, it's not about replacing reference instruments, it's about supplementing the information we can gain from these networks. A great example of this in action is the Breathe London network. This is one of our flagship projects. London actually has a great reference network. You can see this on the left. This is the London Air Quality Network. It's the traditional regulatory reference monitoring network. And you can see they have a large number of sensors in London. That's fantastic. But even this number of sensors are still missing air pollution events. On the right-hand side is the reference network supplemented by Clarity nodes by over 500 sensors. And this is a network referred to as Breathe London. And with this extra information, we can start to see local air pollution events, and the colors are similar to the air quality index, that are occurring in this one neighborhood that's not being captured by the regulatory instruments. So we talked a little bit about where we see the best use cases of low-cost air quality sensors. The EPA has offered some guidelines for their use. These include science education and research, conducting air quality monitoring projects, supplementing regulatory air quality measurements like the example I just showed, and measuring local air quality to better understand sources of pollution. These can kind of be categorized into these three broad categories: hotspots, short-term changes, air quality data for rural areas. Air pollution hotspots are what we're looking at in terms of cities when there's problematic air pollution in one small neighborhood that we need to identify. Low-cost sensors with a highly dense network can start to identify some of these problematic areas. But we can also might be interested in changes in air pollution over time instead of space. Real-time data can help us understand short-term changes in air pollution related to changes in weather or natural disasters such as wildfires. You can think of short-term changes as hotspots in time rather than in space. Then finally, low-cost sensors can help us with air quality data in rural areas or any neighborhood that for whatever reason may not have access to a regulatory instrument. This includes rural areas not just in the United States, but globally. So one of the big things that we think about a lot, and what I really want to impart to everyone in this presentation, is that, again, there's no free lunch. We can't have a cheaper air quality sensor and have it be as accurate and reliable as an instrument that costs tens of thousands of dollars. We have to give something up and we get something back in return. So I want to go over the limitations of limitations of low-cost air quality sensors and what we can do to work with those limitations. First, limited accuracy. Low-cost sensors will simply not be as accurate as regulatory and reference-grade instruments. However, precise calibrations, and I'll discuss that in a few slides, can help close this gap. But in addition to calibrations, we also need to evaluate the low-cost sensor to make sure the data is trustworthy. There's also limited precision. I'll discuss this a little more in a few slides, but for now it's enough to know that between different brands, the same sensor, a sensor measuring the same pollutant, but manufactured by different people or different brands, measuring at the same location may give slightly different answers. Depending on the quality of construction, some low-cost sensors may degrade over time. So there's a question of durability and lifetime. And finally, just to re-emphasize this question of calibration, sensors must be calibrated for different environments and pollutants to provide accurate data, and they must be evaluated and checked for drift over time. So this last point is really important, and I want to dive into it right now. So why do we calibrate sensor data? Why do we always talk about calibrations when we talk about low-cost sensors? All air quality instrumentation has to undergo calibration. That's simply a fact of life. Most instruments are needing to convert electric signals to concentration units. Reference instruments are typically calibrated periodically, and after that calibration, they're assumed to operate well in a variety of environments. Low-cost sensors we cannot make that same assumption that they will operate well in a variety of environments. They need to be calibrated for specific environments and specific pollutant mixtures. So when you get a sensor and you take it out of the box, this sensor was manufactured in some factory. Sometimes it is tested in stable laboratory conditions. Oftentimes, uncalibrated sensors will perform perfectly well in stable laboratory conditions. But that does not mean they'll perform well in outdoor environments. In a sort of generic layperson, colloquial way, I like to think of calibrating low-cost sensors as specializing the sensor for an individual project. We're taking a sensor that performs well in stable laboratory environments, and we are now going to correct it so it performs well in our project of interest. So here's an example. This is in Los Angeles, California. You will be able to look at this data more in detail as part of your homework. But on the left, we can see a time series. The light gray is the raw data or the uncalibrated data, the out-of-the-box data. And the black is the reference instrument. And you can see the uncalibrated data is following along with the reference instrument. When the reference is high, the raw data is also high, but we can see it is offset unacceptably. It is measuring much higher concentrations of PM2.5 that actually exist. So what's going on here is the uncalibrated data is really designed for those stable laboratory environments. It is not designed for the environment of Los Angeles, which has very dry climate with a specific pollutant mixture. We can, however, calibrate this sensor to be specialized for the environment in Los Angeles. And when we do that, we can see in the light blue, the sensor performs much better and is much more similar to the reference grade instrument. We can also have much lower errors over time. So the US EPA has provided some data quality objectives for calibrations and sensor performance. And I'm not going to go over all of these terms. There are a lot of statistical concepts. I really just want to point out this table for a couple of reasons. First, the EPA has provided a number of metrics that look at different aspects of performance, and it's important to consider all of those. Second, these are data quality objectives from the US EPA. The European Union has a different set, and the United Kingdom has a different set. Wherever you're located, this table is something you can discuss with your low-cost sensor manufacturer and discuss with whoever is working with you on your project to see if you are meeting data quality objectives that are suggested by regulatory agencies. Even if in the European Union, there's no reason why you can't look at the US EPA's recommendations. So while I don't want to go through all of the statistical comments on the last slide, it's a great reference to discuss with various project managers in the future. There are two metrics that I do think we need to understand so that we can appreciate low-cost sensor discussions. And these are things that commonly come up when we start talking about low-cost sensors. The first is the R-squared score. This is the squared Pearson correlation coefficient and describes how correlated a low-cost sensor is with a reference instrument. And by correlated, I mean when the reference goes up, in concentration, the sensor also measures an increase in concentration. And when the reference goes down, the sensor goes down as well. Very importantly, the degree that they go up and down needs to be described by a straight line. So that's what I'm showing in the example on the right, where the reference instrument measurements are on the x-axis, the low-cost sensor on the y-axis. The red line is the line of best fit. And what I want to point out is that this line is a straight line. So a high R squared means they go up and down the same, and it is a straight line, not curved, but straight. Now, you could go up and down the same and be offset by 10 micrograms per cubic meter, minus 20 or 100, and still have an R squared of 1 or perfect. So we need a second metric to describe the degree of offset. This is often described with the mean absolute error, which is showing the average difference between the low-cost sensor and the reference monitor. And here, the lower the better. If you have a mean absolute error of 0, that means on average, your errors are 0. Root mean squared error is something that often comes up as well. There are subtle but important differences between the mean absolute error and the root mean squared error, but they get at the same thing. These are both describing the average error of the low-cost sensor. Now, there is a common misconception and source of confusion, and I'm just going to highlight that very briefly. When we talk about R squared scores, the higher the better. When we talk about error scores like mean absolute error, the lower the better. You want your error to be 0 and your R squared to be 1. If you have that situation, your sensor is performing well and you're collecting useful data. But there are other situations, of course. If you have a high error and high R squared, you likely need to recalibrate your sensor and offer a correction. If you have low R squared and low error, oftentimes that's simply because you have a very low concentration range, and we recommend increasing your evaluation data. And then finally, you can be in the unfortunate case of having low R squared and high error, and this often indicates a problem with the sensor. Next, there's also questions of accuracy and precision. And just to briefly go over these, accuracy is when a low-cost sensor and the reference instrument are measuring the same quantity. Precision is when you have two low-cost sensors and how different or similar the sensors are to each other. So you can have situations when you're both accurate and precise, neither accurate nor precise, or somewhere in the middle. So I've talked a little bit about some metrics, but how do you actually get the data to look at those metrics? This is a really important concept. It's called a co-location study, and we recommend it with all of our projects. In a co-location study, you are simply co-locating your sensor with the reference instrument. And by co-locating, I mean put them in the same place, let them sample the same air. And that's an example is being shown on the left. This is London. You can see several clarity sensors, and those can be identified by the small black solar panels. And they're on top of a reference regulatory site, so they're all measuring the same air. One thing I think is vitally important for all projects is to leave at least one low-cost sensor co-located with the reference throughout the course of the project. So in this way, we can monitor not only conditions at the start of the project, but after a month, after 5 months, after 2 years, and keep an eye on data quality. So co-locations are extremely important, and we highlight them in their own section on the Clarity dashboard. This is something you can explore more in the homework. I'll step through all of these panels very briefly, but first to point out, we at Clarity have both the uncalibrated or raw data and the calibrated data, and we can take a look at how the calibration performed and how it improved the data. So this is our example from Los Angeles once again. We had a high R squared to start with, that's great, but we had an unacceptably high mean absolute error. After calibration, where we take the sensor that probably performs well in stable laboratory conditions, make it specific for the Los Angeles climate and pollution mixtures, we now have dramatically improved our mean absolute error. R squared was already fairly high. Remember, we can't go higher than 1, so we've still improved it by a small amount. So next, we have a number of diagnostic panels that I'll briefly step through. First is a co-location histogram. So this on the x-axis is the PM2.5 mass concentrations, And on the y-axis is the number of measurements when the concentration was between 0 and 10, 10 to 20, 20 to 30. Now, this is very important because we want to measure not only fairly clean conditions like 0 to 10 micrograms per cubic meter, but also conditions that are unhealthy to breathe, so such as 10 to 20 and 20 to 30. So with this plot, we can monitor if we're measuring a representative sample in Los Angeles over the course of the co-location. Next is the time series plot. This is the most intuitive of the plots. The measurement of pollution, micrograms per cubic meter, is on the y-axis, and time is on the x-axis. And now we can see the clarity sensor and the reference instrument as they move over time. Next is a scatter plot where we have one sensor on the x-axis and the other sensor's measurements, or I'm sorry, the reference instrument on the y-axis. And here, remember, we want to look for a nice straight line comparing the two instruments to show that there's a linear association between the two of them. And finally, we can take a look at our error over time. So this is showing error on the day of the month on the x-axis. And we can see at the start of the co-location, error is fairly low, less than 2. It increases to about 6 during a period of high concentrations and goes back down to about 2. The average error over time is about 2 micrograms per cubic meter. This is something you can continue to monitor over the course of the project to see that errors are not increasing over time. So finally, I mentioned this a few times, but I want to return to it once again. One of the great benefits of low-cost air quality sensors is not in replacing regulatory instruments and having low-cost sensors work on their own. It's about supplementing infrastructure that already exists. It's about supplementing reference-grade instruments, and even in certain projects, like the example being shown on the right, you can combine the reference instrument with the sensors with modeling and statistical and physical modeling to have an even better understanding of air pollution in a specific environment. Great. I really appreciated everyone taking the time to listen to me talk. It's been a lot of fun. I wanted to give a shout out to Sean, who's giving the next panel on use cases and lessons learned from air quality monitoring projects in 70+ countries. This will be a bit more specific in depth than the overview I've provided, and I'm really excited to hear Sean. He's a great speaker. Before we go to Q&A, I think Ryan will give a little discussion on the homework we've assigned to you. It'll be a really fun where you can explore the dashboard and explore some of the data concepts we've discussed in this talk. Ryan?
Great. Yeah, thanks, Jack. And thanks for the excellent presentation. That was a great intro to, both the potential and some of the limitations of air quality sensors. And yeah, thanks for digging into the calibration side of things. I know that's a topic that we heard a lot of interest from the audience on. I'll keep this really brief, but yeah, with the homework assignment. So we'll follow up tomorrow, sharing a brief document explaining how you can access the demonstration dashboard account. So the dashboard is how Clarity's customers and partners access their data. Our software team has been kind enough to set up a demonstration account for our bootcamp registrants. So we set this up specifically for all of you to be able to complete this homework assignment. And I do want to give a shout out to Los Angeles Unified School District who provided the data. So this is actually a clone of their real live data from the 200+ sensor network that Los Angeles Unified School District has with us down in LA. It's just a subset of the data, but good to be aware that it's coming from real live Clarity sensors. So yeah, that's all I have on the homework. And we do have quite a few Q&A topics coming in. So yeah, let's jump to that. So yeah, one question that I think might be of interest for people is from Matthew. And Jack, his question was, is the type of particulate matter also important for health beyond the size?
Matthew, great question. That is an ongoing and hot area of scientific research currently. So first, PM 2.5 has been shown consistently to be associated with poor health outcomes. That's where we have the most stable, reliable scientific evidence. Now, we certainly think that the composition of PM is important for health outcomes. So for instance, sea salt aerosol or sea salt particulate matter is probably not going to cause a large negative health outcome, whereas black carbon, soot, organic carbon probably is bad, even worse for our health. So that said, even though we suspect that, and there is emerging evidence that composition is incredibly important for predicting health outcomes, the level of science and research is still ongoing. It's still an open question, and we certainly can't quantify it yet. But that is certainly where the field believes the science is going. So that's a great question.
Great. Thanks for filling us in there, Jack. And kind of a follow-up, on the effects of pollutants. Do primary and secondary pollutants have the same effect? And if it varies, what could the cause of that be? I don't know if we know if primary and secondary pollutants have different health effects, but is that something that you want to weigh in on, Jack?
Yeah, absolutely. This is also another active area of research. So we mentioned primary and secondary. This also applies to particulate matter. Some particles form in the atmosphere, and also a number of primary particles may undergo chemical reactions and their composition changes in the atmosphere. Once again, there have been a number of studies that have shown that secondary aerosols or secondary particulate matter do have a higher health effect. But once again, it's an active area of research. We think that the increased for organics that have very complicated chemistry, increasing the oxidation of compounds does increase the negative health outcomes, or that increases the toxicity. But once again, it's an active area of research. There are certainly likely toxic particles that are primary as well. That's another great question, another very important area of research.
Great, thanks, Jack. So moving from health impacts to, I guess, use cases for low-cost sensors, we have a question here that I think is going to be a tough one, and maybe something that we'll, weigh in on more during the network design presentation. But somebody's asked, how wide of an area could one low-cost sensor cover? Is that something that you're comfortable with weighing in on, Jack?
Yeah, sure. It really depends on the type or which pollutant we're interested in the spatial distribution of that pollutant. PM 2.5 tends to be a little bit more regional over a city, whereas NO2 often varies block by block. NO2 is highly related to traffic, so you will have much higher concentrations by a road as opposed to a park. Ozone is a secondary pollutant and is much more regional, so you may need fewer ozone sensors in a city compared to PM 2.5, where you need slightly more, and then even more for NO2. There's no one specific answer for how large an area one sensor can measure. It comes down to the type of pollutant and the sources. If you have a lot of different sources in one area, you need more sensors. If you have fewer sources, perhaps you're in a more regional area and you need fewer sensors. It really depends on the project, and thinking about that's a really important step for setting up an air quality monitoring network. Great
answer, Jack. And there's certainly a lot of subtleties that make it difficult to provide a numerical answer to how much area a sensor can cover. But the good news is we will be diving into that on the network design session later this month with Maggie, who just recently completed her PhD dissertation looking into this topic. So if you're interested in that, that area of how much coverage a sensor or network of sensors provide, make sure to join that network design session on the 21st. So Yeah, another question kind of in that vein is, we talked about hybrid networks and the relationship between reference monitors and sensors, but actually also from Matthew, great questions. So can several well-calibrated low-cost sensors in the same place substitute a reference instrument by averaging the measures?
Certainly doing that is a way to increase the quality of the data. Having more of them and averaging them out, it assumes the errors are distributed randomly, which is often a fair assumption. I would never go as far as say it replaces a regulatory instrument, but certainly having several of them at the same locations will increase data quality. And that's certainly one way to reduce errors and begin to increase data quality. On the other hand, if there's an interference with the sensor, if all sensors perform a little bit worse in certain humidity, certain temperature ranges, you may have all sensors being biased in the same direction. And in that case, you wouldn't improve your data. Well, you'd likely still improve it a little bit, but not to the point of a reference instrument. So I think it's still important to consider influences that may, or interferences that may influence all of the sensors. But Matthew, you're definitely thinking along the right path there. That's a great comment.
Great, thanks, Jack. And following up on that, actually, Matthew had another question on this topic, and Anna has a similar one. So I want to read Anna's question. Is related to the role of a reference monitor in the calibration process. So Anna's question is, I will develop a project in a high relative humidity city without a reference AQ monitor. Can I use a sensor compared with a reference monitor in another city?
Oh, that's a great question. My advice to you would be to try to have your reference monitor in the other city as similar to the conditions as you will have in the city that they'll be deployed. That's where you'll get the best response and the best calibration conditions, having them as similar as possible. It also depends a little bit on your pollutant of interest. So NO2 sensors, ozone sensors, these gas sensors, their composition, NO2 is always going to be the same. It's 2 nitrogens, 1 oxygen. I'm sorry, I did that backwards, but you see my point. In that case, you're just correcting for the relative humidity interference. For PM2.5, you have both the different compositions of particulate matter as well as the relative humidity. And the relative humidity in that sense is just how much water is on the particle, so the composition change. So if you expect your PM2.5 composition to be the same in the 2 cities, then you may have a possible way forward. But if you expect them to be similar relative humidities, but different chemical PM compositions, you may run into problems there.
Great, yeah, and so always ideal to have a reference monitor in the same location, and or at the very least with a very similar climate and environmental conditions. But yeah, thanks, Jack, for weighing in there. So we have a question here from Robert. Can you define the difference between calibration and co-location?
Yeah, absolutely, Robert. Co-location is simply the physical placement of the sensor and the reference. So we're just putting them in the same place. Calibration is using the data you got from the co-location to make corrections to the low-cost sensor. In addition, with the data you have from co-location, you can also use that data to evaluate the sensor. So the important difference is co-location is physically putting them together to generate the data you will use to do other things. Calibration is one of the things you can use with the data from co-location where you correct the sensor. Now, not all calibrations come from co-location. Sometimes you will see low-cost sensors that were only calibrated in a laboratory or in the factory. We are often very suspicious of these because they're not meant to be deployed outside of those laboratory conditions, but you could have a calibration that occurred without any co-location.
Great, thanks, Jack. So we've got a lot of open questions and limited time here. So I'm going to take one of them real quick. So, Ahmed, do you have any success stories in India or Egypt? We do. We had a network in Bengaluru, and we do have a blog post on our website about that project. So happy to follow up with that link. If you join the Slack group, Ahmed, and reach out, I'll be happy to share that link with you. And yeah, I would encourage everyone to check out our website to, see case studies of some of the projects we've done around the world. Let's see, probably only have time for one more question here, Jack. Are there any that are sticking out to you that you want to make sure to answer, or anything else that you, want to make sure to cover to wrap up here in the final minutes?
I haven't been able to look through them too much, but I saw one question in the chat about concentration ranges of low-cost sensors, and especially for poor ambient air quality in developing countries. That's a really important application to be able to measure ambient air quality in developing countries, especially places that don't have the infrastructure that the EPA monitoring network has. Often these sensors work quite well in higher concentration ranges. The important part is to simply calibrate them for these higher ranges so that those sensors, we can properly correct and continue to evaluate them. Some sensors, like gas sensors like NO2, will actually perform much better at higher ranges. If you have conditions of 50 to 100 ppb of NO2, you'll likely have an even better performing NO2 sensor, because you will have a high signal to noise range. So I think ambient air quality in highly polluted areas is a great use of low-cost sensors. The only thing to keep in mind is to make sure calibration evaluation is under similar conditions so we can continue to monitor them.
Great, thanks, Jack. And yeah, we have quite a few open questions still. Looks like about 40. A lot of them related to calibration and co-location. So what I'm thinking is, we'll take the list of open questions and take a look through them. And Jack, maybe we can touch base and see if we can put together some brief written answers that we could share in the Slack group. And yeah, I think, maybe even a bit of an FAQ on some of these common calibration and co-location questions. So yeah, I think we're a minute over, so we will be wrapping up for today. Just want to say thanks again for everyone, for joining this session, for your active participation. This is probably the most active Q&A we've seen in any of our webinars to date. And yeah, just really thanks again to Jack for an excellent presentation, and clearly people are very interested in this topic. So we'll do our best to follow up with the pending Q&A questions offline on the Slack channel. I believe Clemence has shared a link in the chat to join the Slack, and we'll also follow up again via email with a link to join the Slack channel for the Air Quality Sensor Bootcamp. So yeah, we'll wrap up for today. Thanks everyone for joining, and thanks again, Jack, for filling us in on this topic.
Absolutely. Thanks for your questions, everyone.